Hello friends, welcome to the online course on applied time series analysis. This is a nearly 45 to 50 hour course. In this short video, we will give you a quick overview of the course, and after listening to the video, you can make a decision whether this course interests you or motivates you to pursue this subject. It falls under the broad area of what we call as data sciences today. But as far as the history of time series analysis is concerned, it's nearly 100 years old. In fact, if you go into the other aspects of time series analysis such as estimation and so on, it's much more older than that. So let me give you a quick idea of what is time series. If you look at the title of the course, you have applied time series analysis, and applied part simply says that we will give equal or a bit more importance to practice than theory, but definitely we will talk quite a bit on the theoretical aspects because they give you the foundations for practice. And then you have time series, and then you have analysis. So let's understand what a time series is. A time series essentially is a ordered collection of data, of numbers, observations, and this ordering could be in time, could be in space, frequency, or multidimensional, that is time and frequency and both. So to give you a quick example here, in fact I have 4 examples from different domains. That is one important thing that you have to remember, that time series is fairly interdisciplinary. In fact, it cuts across all disciplines. In the first example here, I have a temperature series from an industrial dryer. So this is coming from engineering domain, and then you have the readings from an automated weather station of wind speed from a certain geographical region. So this comes from the atmospheric domain, and on the bottom left here we have the Swiss stock market index over a certain set of years. Typically this is what interests the students a lot because it has got to do with finances. So obviously this comes from business or econometrics, and the fourth one that we have here is the reading from an experiment, ECG experiment. Most of us know what is ECG. It comes from the biomedical domain, and it has got to do with the condition of the heart. So here you have 4 different series. On the x axis, in all of this, the x axis is time, that is the independent dimension is time, and on the y axis you have amplitude. So this is a typical time series that you would run into, and what you should quickly observe is that each of this time series has different features. On one hand, so for example, if you take the bottom left plot where you have the stock market index of the Switzerland, you see that there is a trend, and this trend could be linear or quadratic and so on, and on this trend riding you have certain irregularities, which is what we call as random changes. On the other hand, if you look at the wind speed, which is diagonally opposite here, how well I don't know you can see, but visually if you pay attention a bit closely, you will see some kind of an oscillatory feature, or you can say seasonality, and this is to be expected because of changes in the atmosphere. And on the top left, we don't really see particularly any oscillations, at least not by visual inspection. The time series analysis tools will help us figure out if there are oscillations or any other features and so on. But this is a different kind of series. And then you have ECG, which has completely different features. There is no particular commonality except maybe for the periodicity. In fact, if you turn to the literature, it will tell you that it has what are known as the features of a non-linear time series. And we can go on and on. We can draw examples from different domains and keep talking about the features. But hopefully now you have some idea of what a time series is. It is these kinds of time series that we will analyze. In fact, you can even look at broader examples. So for example, here on the left, I have measurements coming from a process, in fact again from an engineering process, where I am looking at measurements from 12 different control loops. So this we say is a multivariate data because we are looking at many variables simultaneously, unlike previously what we did. So on the left hand side you have the time profiles, and on the right panel of this figure you see that there are some other trends or some other curves there. They are actually nothing but the power spectra of these respective time profiles. And for those of you who do not know, power spectra are obtained by taking the Fourier transform. So what we have done is we have taken the data in time domain, transformed it to Fourier or frequency domain, and constructed the power spectra. So what this power spectra does is it highlights the frequency content or any oscillatory nature. So if you pick any of the power spectra here for any of the variables here. Let us see here, we have this variable here where I have positioned my cursor. You can see there is a peak. In fact, there are peaks in almost all of them, correct? And this peak is an indication of the presence of a periodicity or oscillation, oscillatory nature. In fact, interestingly, this itself is time series analysis, where you are analyzing the given data on the left hand side, time domain data, to figure out what is the periodicity or if there is a periodic component present. A lot of times we may not be able to, in fact most of the times it may be very difficult to detect the periodicity by visual inspection. Only under some very special clean situations, clean data, single periodicity, we will be able to figure out by visual inspection, but otherwise by and large we have to turn to mathematical methods such as Fourier transforms and so on to analyze any signal for the presence of periodicity. So, that is a big part, a significant part of the course. We will talk about how to detect periodicities using Fourier transforms, but we will not be looking at multivariable data per se. And in the center you have an image. So, this is a completely different thing. There is no notion of time here, yet we call as time series, but time is very generic here. This is simply data in a two-dimensional space. It is spatial data where each point that we have here is a pixel. It is the value of the pixel between 0 and 255. One could analyze this image for many things. I could analyze the image for certain patterns, certain features and so on, and we all know image processing is a very big branch of signal processing. We will not be again looking at two-dimensional signals in this course. This is just to give you a broader perspective. And finally, we have this image which is pretty fresh. I have taken this image from the Indian Meteorological Department website, IMD website. This is a 3D image of the earth as seen by the satellite, and I do not know how many of you are following. There is a cyclone by name Varda which is supposed to be hitting the southern part of India, the east coast of India, and interestingly this itself is a very interesting time series analysis problem. For example, over the last 1 week there are so many models that are trying to predict where this cyclone is going to hit along the east coast. Is it going to hit at Visakhapatnam or at Kakinada, Nellore, Chennai? Where is it going to hit? Some models would say, well, anywhere between two regions. So, that is called interval prediction, and some models are more precise. They would say, well, pretty much near Chennai or Nellore and so on. So, this is a very interesting time series analysis problem, and in fact, if you turn to the atmospheric or the meteorology literature, you will find enormous number of time series applications. Again, we will not be looking at such data, just to excite you and get you into the subject. So, you can have time series that are univariate, multivariate, multidimensional, that means time, space or frequency, and even in a transform domain. That is why we have selected these examples for you. So, that is the time series part, and I briefly already talked about analysis. So, let me now very quickly talk about the typical objectives that one encounters in time series analysis. So, now we are talking about the analysis part. One of the foremost objectives of time series analysis or foremost exercises is forecasting. All of us are interested in prediction, whether it is that of the climatic phenomenon or an engineering process or our own lives. We are always interested in forecasting. So, that has interested man for centuries, but if you turn to the open literature, you will see that there is a lot of work that has been done on prediction theory and continues to be done over the last 100 to 150 years at least. And then the second most important exercise that you would run into is for periodicity detection. We have already talked about it, and we know why. In almost every sphere, whether it is engineering, medicine, for example in the ECG, I would like to know how frequently those spikes occur, because that has got to do with the heart's condition, in fact the rhythm of the heart. If there is a break in that rhythm, then something is called arrhythmia, and it's that means the heart is not functioning as it's expected to be. So, periodicity detection is of interest in every domain, engineering, medicine, atmosphere and so on. We will learn in this course how to detect periodicities, and then you have classification or pattern recognition as the other prime objective in time series analysis, where given data we would like to classify into, or we would like to categorize, saying that this belongs to, for example, if I give you ECG readings of different patients, you would like to classify this belonging to a healthy patient or an abnormal heart and so on. In this course, we will not talk of classification or pattern recognition. Typically, you would learn that in a machine introduction to machine learning course or a more advanced time series analysis course. Now, in the process of figuring out how to forecast given a series, for example, the Swiss stock market index, I would like to know where the stock market index price is heading, or periodicity detection or classification, one encounters many sub problems such as filtering. You want to get rid of a lot of noise, or you want to only focus on a specific component of the series, or you may want to recover missing data. There are many a times the situation that you have missing observations, and although I place parameter estimation towards the end, but as we say, it's last but not the least. Parameter estimation is an integral part of every time series analysis exercise. What we mean by parameters is, could be statistical parameters, mean, variance, correlation, anything that you take, or model parameters. When we build models such as ARIMA models or autoregressive models or any other model, even neural network models, the weights in the neural network, these are all, you can say, some kind of parameters or unknowns. You would have to estimate those. Every time series analysis exercise involves estimation of some unknowns from the data and some other known knowledge. That is something that we will spend a significant amount of time in this course, where we will discuss estimation theory, and I will quickly talk about that. Let me just tell you, and by now you must be also realizing that applications of time series analysis is just huge, it is very broad. There is no discipline that you would see time series analysis not being applied. Now, one thing that one has to watch out for is, you take any of these fields, whether it is you say, for example, engineering applications or astrophysics, or you take meteorology and so on. You have to watch out for a very important division, which is got to do with analysis of deterministic signals and analysis of random signals. And we will define what a deterministic signal is, what a random signal is in the course, but loosely speaking, deterministic signal is one which you can predict accurately, and a random signal is one which you cannot predict accurately. For now, that definition should suffice. In this course, predominantly we will only learn how to analyze and forecast random signals, with one exception where we talk of periodicity detection, where we will spend some time on detecting periodicities in deterministic signals. But by and large, we will look at random signals and sometimes a mix of deterministic plus random signals, and that is extremely important, because the methods and the estimation procedures that you use are different depending on whether you are looking at a deterministic or random signal. But generally the subject is known as time series analysis. In some fields, this is known as statistical signal processing, the time series analysis, or random signal processing, sometimes DSP, applied DSP and so on. And if you are looking at an applied DSP course, you may actually see more emphasis on deterministic signals, but in a statistical signal processing course, the emphasis is on random signals. So, you can think of this course as being pretty close to statistical signal processing. So, coming back to our discussion, there is not a single field or a sphere of analysis in which you will not see random signal processing. So, in this course, we will learn some of the basic concepts of time series analysis. Occasionally, we may talk of a few advanced concepts. The objective is to equip you with foundations of time series analysis, so that you take these foundations and you are in a good position to understand the rest of the literature with self reading. So, in particular, we will focus on linear univariate random processes, and we will talk about so called stationary processes most of the time, with some excursion to non-stationary processes, and maybe sometimes bivariate analysis, but beyond that we will not go in this course. And we will focus on both time domain and frequency domain analysis. In the time domain, we will be interested in forecasting, where we will build the so called very well known ARMA, autoregressive moving average, or ARIMA, autoregressive integrated moving average, and SARIMA, seasonal ARIMA models. These are found everywhere in time series analysis. And in the frequency domain, we will learn how to analyze the periodicity of a signal. Very often this frequency domain analysis is called spectral analysis. So, through the use of spectral density functions, we will understand how to detect periodicities in deterministic and stochastic signals. And finally, as I said earlier, we will learn the basics of estimation theory, where we learn concepts such as bias, variance, consistency, efficiency, Kramer-Rouse bound and so on. Those are properties of whatever method that we use for estimates and the estimates themselves. And the methods for estimation, namely method of moments, least squares, maximum likelihood estimation and Bayesian estimator. So, this will be these are the topics under estimation theory that we will talk about. So, before I conclude, I just want to say two things. One, on how this course is pitched. Yes, we will talk about theory, but the emphasis is on interpretation of the theoretical concepts. We may avoid a lot of proofs. I will show you from time to time how to practice some concept that we learn in the theory through the use of the software, which is R. And an important thing to remember is time series analysis is both theory and art. So, there is a science and an art, which means there is objectivity and there is subjectivity. So, the art part comes from experience. You will find that there are gray areas in time series analysis. There are no definitive answers. For example, if I am fitting a model, I do not know what is that order of model that I have to exactly fit, because there is no one answer. Then I will have to actually figure out by experience and by going through some following certain guidelines. So, please remember, there is going to be theory that we can teach, but the skill part comes from practice, and that is where we will need a computational tool, and we will turn to R, which is a software for time series analysis. And it is an integrated software package. It is an open source, most importantly, it is free. It is available on all 3 platforms. A fantastic piece of software written by community at large across the globe. Several hundreds of volunteers participate in the development of this package. It has certain powerful graphical and numerical analysis tools, particularly oriented for statistical data analysis. And you can easily install add-on packages. The base package comes with certain functionalities. There is a very systematic way of doing it. We will have a tutorial for you if you are new to R, but by and large R is becoming very popular. So, you can also learn R and at least get into the basics. There are many websites that give you an intro to R. There is something called R Studio, which offers a fantastic graphical user interface. It is not R itself, but it assumes that you have already installed R and gives you the user interface, a very convenient and powerful interface. We will use this R Studio extensively in the course. And as far as the books that we follow are concerned, I cannot recommend a particular book, but I have a list of references for you, and among this I will highlight 2 books to begin with. One is a book by Shumway and Stauffer, which assumes that you have some background in statistics. It assumes, for example, you are good in probability theory and have some idea of what is a density function, moments and so on, and then builds upon that. And then you have the other book, which is authored by me, although it's been originally written for system identification. System identification is an extension of time series analysis, where some causes are known, not all causes are known. These are exogenous signals, external signals. So, not much different from time series analysis. There are parts of the book that are very relevant to this course, and when I put up the course outline, I will identify which chapters are relevant to the course. Apart from this, of course, there are excellent, fantastic books which you can read. For example, I strongly recommend the book by Priestley. It is a big reference book, but very easy to read, very clearly written, and Priestley is a big name in time series analysis. The book by Hamilton is also good, but it is pretty dense. Then you have the book by Brockwell and Davis, Introduction to Time Series and Forecasting, that also I recommend, and then the standard book by Box and Jenkins, but again I have included this for your own reading. Okay, so, hopefully you have some idea now of what this course is about. It has been a bit lengthy introduction, but it is worth it because the subject is such. So, from this you can gauge that the subject is broad, and now you can decide whether you are interested in the course. The prerequisites would be a basic course in probability theory and statistics. To the basic level, that you have a knowledge of what is probability density functions, continuous and discrete valued random variables, some knowledge on expectations and so on. There is an online course that was offered, which was titled Introduction to Statistical Hypothesis Testing. which goes through, which gives you this elemental introduction and then talks about hypothesis testing. I strongly recommend that you download those video lectures. It is about 10 to 12 hours of videos, but it is worth it, and therefore, just download it from the NPTEL website, those videos, and it will give you the sufficient background to get started. And as I said earlier, we will do a quick review of what are density functions and expectations at the beginning of the course. So, that is one requirement, and some basics of linear algebra will help. Okay, so with this I think we will wind up, and I wish you good luck. So, hopefully you are interested now in enrolling for this course, and also that you will walk with us until the final exam. Thank you.